Hi, this is Bill Geyer with Ardupilot, and I'm here today to brief you on the work that was done with the System Identification Web tool. Today I'll go over the background behind system identification, talk about the tool development, and then also go over the tool features as well for both the transfer function estimation and the linear state space model estimation. And then I'll go through a demo of how you would set up both the transfer function and the linear state space model to be solved. All right, so a little bit of background on system identification. So basically, this is a technique to determine aircraft dynamic models from a time history data. This can be used for any type of system, but in many cases, it's used for vehicle flight dynamics or even subsystems like actuators or engines. This can be done with both time and frequency domain test techniques that they use to determine these models. And time domain techniques are better suited for identifying nonlinear models. Whereas this frequency domain, as you'll see here, we're mainly just using this to identify a linear model, meaning that uh, that basically there's no um, no acceleration limitations or rate limiters that are going to cause kind of a nonlinear behavior within the system. So for this, it requires time history data uh, set that covers a range of dynamics to be modeled. So if you want to model both, maybe the low frequency, like the phugoid, long-term mode of a motion, and then also model the the short-term modes of motion, like the control response or the short-term stability of the aircraft. So, you need to have data that would kind of demonstrate those in the time history domain so that it can actually be able to develop the model for that. Um, so again, you could use random maneuvers, as it says here, to kind of excite those dynamics for the short-term and long-term responses. In many cases, in my experience, mainly we use frequency sweeps that range over the frequencies where those modes of motion are contained. But you can also use inputs like 3, 2, 1, 1 inputs if you're familiar with that. Excuse me. Um, so it's just a number of different ways that you can use to excite the dynamics that you want to represent in this model. So like I said, for the frequency domain technique, uh, or what we used for the web tool was the frequency domain technique to determine the state space model and to look at um, the transfer function estimation. Um, so kind of big distinction I want to make first about state space models versus physics-based models. So physics-based models essentially use the properties of the vehicle to calculate the forces and moments on the vehicle to then produce the dynamics. Because of that, and depending on how well the physics are that are used to model the vehicle, you're able to simulate it throughout the flight envelope, and it actually is more suited and better suited to represent the nonlinearities that may be involved in the dynamics of that particular aircraft or vehicle. Now, like it says here that the flight test data is required to validate the model, and you'll need a substantial bit of flight test data to try to ensure that you've adequately modeled the physics of the vehicle or the dynamics of the vehicle. Whereas a linear state space model is mainly based about a trim point for a given trim condition. And you generally would develop one model per trim condition. You can stitch those models together to make it a full envelope, a flight envelope model. Um, but the way state space models are developed is through using flight test data that, like I talked about before, any type of dynamic maneuvers or frequency sweeps typically is what we use to then determine the state space model. And then you kind of along with that is you just can't have, you know, everything fully populated matrix. It's often good to be familiar enough about the dynamics of the vehicle to kind of state a specific model structure that would then help uh, limit or quickly pare down the identification to make it a little easier to identify the specific vehicle's dynamics. Um, Right, so it's only developed for one trim condition. Again, like I said, you could take multiple trim conditions and stitch them together to get a full flight envelope. And basically, it says it's a time invariant linear model, which means, you know, we're saying um, that the system doesn't change over time. And what that means is, again, is if you have any type of saturations or uh, in certain control throws, or if you have, acceleration limits that are thrown in there, or rate limits that are thrown in there, those change the dynamics of the system and therefore could change the derivatives or could change the model structure or change the system. And so that makes it difficult for this type of technique to model that. So basic structure for a state space model is shown here with the top equation where x dot is equal to this A, your stability matrix times the states x plus the control matrix B times your control vector U. And so again, this is all kind of in a matrix form, and this is your basic equation dynamic equations here in the top equation. And then the second equation here, y is equal to cx plus du, essentially defines kind of the observable states or observable variables from your control and state variables. So again, if you're only able to observe the dynamics like pitch and roll rate, then you'd have a matrix here that for C that would then define kind of what variables of the states would then equate to the observed data that you recorded or were able to collect. Um, And so the form that we use for the state space for the web tool here is where we actually have kind of in this equation above here, we've divided through by mass to get for the A matrix and B matrix here. We've left mass out front of x dot. And so basically, um, it's a little bit that there, it's put together differently. And you can see the observed variables are set up a little different, looking at both the states and then the first derivative of the states. And so that is a little bit different, but you've shown over here how you can kind of convert uh, what we have here in this form that we use in the web tool to the matrices that are used up in your standard state space setup. The transfer function, these describe relationships between single input and single output of a system. So let's say it's your lateral stick to the lateral roll rate or to the roll rate of the vehicle. So this could be described as a transfer function and for a, and, can have this kind of a, numerator and denominator described as up here in this transfer function. So they're great for investigating dynamics for one axis. They can allow you to look at kinematic consistency between maybe your different variables that you have that you're collecting. So roll rate and roll attitude. So you can basically look at that relationship to determine how well your EKF is determining that roll attitude from the roll rate and doing that integration. Um, and then also uh, you can use this transfer function that so that you can then maybe determine starting values for some of your state space um, variables or derivatives. So you can get kind of useful information from it to then start and then make better guesses at your state space solution. As far as development of the tool, I'd like to thank our Google Summer of Code student, Astik Srivastava. And he was co-mentored by myself and Pete Hall, and so he did a great job with this work. Certainly a pretty monumental task to try to put together a state space um, web tool over one summer. So some of the accomplishments that he had here with his Google Summer of Code. Um, During that time was that he was able to put together the System ID web tool that uses log analysis and is able to extract a model from that. And then also he did Lua script for frequency sweep generation for RG where RGCopter has that System ID mode. RG doesn't have this type of a mode in it, and so he was able to develop a Lua script that helped allows them to go ahead and do sweeps in RG plane. Some of the challenges he faced, one of the things was finding a system ID solver in JavaScript. And so what happened was he was able to capitalize largely off the work from GitHub user that has this PY aircraft ident, which is essentially um, a Python code that provides system ID solver. But then he was able to use this diode library that's able to run Python algorithms in JavaScript. So it's a little slower when it runs, but we have at least a basic capability now that we can then capitalize and improve as we go forth. The other thing that was challenging was designing better search methods into the solver algorithm. It uses the Python SciPy library for the solver, um, but and we were able to, or I should say, he was able to uh, modify the inputs to that solver to help provide better solutions. So what are some of the features of our web tool? Uh, it's designed to take the frequency sweeps from the system ID mode. If you're not familiar with that flight mode of RGCopter, you can go onto the wiki and look at that system ID mode uh, and get familiar with that. But basically, it's utilizes that data to develop linear models of the air vehicles, so multi-rotors and helicopters alike. So and for that you can estimate transfer functions, you can estimate the state space model. Um, so as it says here, anytime history data can be used, but frequency sweep data is probably going to be best to try to develop these models. And one thing to be cautious of is be sure that all your signals are sampled at the same rate over the whole time range that you're using to do the state space estimation or for the transfer function estimation. Be aware that going from another mode into system ID mode uh, a lot of like the rate logged data and the attitude log, the ATT messages and the rate messages, they will change their sample frequencies and therefore would affect your ability to use that data. So be sure that whatever mode you're in, you stay in that mode for the time of interest that you're trying to get the data. I would just recommend just using the system ID mode and just choose data within the system ID mode run. It has to be a contiguous set of data, so there can't be any switches over to another mode and back to system ID. You have to be all in system ID for that time range that you're interested in using. Um, So other features of the transfer function, it allows only one contiguous set of time history data. So unfortunately, you can't concatenate multiple sets of time history data. You'll just have to use the one system ID mode run. Um, and one of the features, another feature is that you can specify the order of the numerator and denominator, and only include powers of S that represent your model structure. So for what I have shown here is a model structure for a multi-rotor pitch or roll axis. And so it's second order on the numerator, fourth order on the denominator, but in the numerator, it doesn't include the constant term. And then when you look at how you'd put it into um, the fields within the tool, just remember that the exponent is represented as a double asterisk before the exponent number. And so you basically put together this particular numerator denominator would be represented in the fields as shown over here. You, as the user, can specify your frequency range that you want to have it fit the transfer function for. Your initial guess should be the start and stop frequency of the system ID sweep, but you may want to further limit it that and further kind of draw that in from those start and stop frequencies to get a better fit and a better cost on it. Um, and then also kind of something to condition the data, you can specify a cutoff frequency for the anti-aliasing filter. So there's a low pass filter that can be applied to both the input and the output data that would condition it so that you can be able to get better results. You probably want to set that above, certainly above the highest frequency that you want to fit for. Um, And so that should basically remove a lot of the noise and help provide a better fit. So how do we use it? So here's the top of the tool that you would see in the web tool. And so you would basically come in and choose the file using that button. Once you choose the file, then you could then set the time range in these two boxes here, start and stop time in seconds. The data shown down below here, and so basically you would look at your data. You can see there's a number of different sweeps in this time history data. One was in the blue is roll, one was in pitch, and the other one was in roll. So I'd basically choose probably from time 300 to 400 here, or maybe 300 to 370 for this particular time range for the system ID mode, and that would be one set of contiguous data there that I could use. Then you'd scroll down and you'd see the choice of whether you want a transfer function or state space. So you'd choose transfer function, and then fields would appear below that. These fields would appear that you would then fill in. Um, so there you'd fill in the input signal. So you choose from the available messages. Here we're going to choose the rate message and the R out, which is basically the input to the motors mixer um, for the roll axis. Then you could go to the output for your signal, and that's going to be the SIDD message, which is basically the system identification data that's taken. And again, the rate message, the ATT message, and the uh, SIDD messages are all in system ID mode, are all sampled at the same rate. And you can change the multiplier for that rate through the log bit mask. So you can look that up. It's in the system ID mode wiki. So here we chose the roll gyro. And again, remember that the sysID roll or gyro data is pre-filtered, pre-INS filtered, and it's generally what you'd want to use to get a good model. And then it is in degrees per second, so we are using the multiplier here then to, as I've shown here, you can use a multiplier then to convert it to radians per second, and so that's what's being done here. There is this gravity compensation feature, and I'll describe in a minute here what that does. We talk about that again. So now we can take and put in the fields for our numerator. And again, remember the double asterisk is what is used to indicate a power for S. And so again, I use the roll multi-rotor transfer function structure. And then for the numerator and denominator. And then we have to list the variables like in your fields here, you're going to use like A, B, you can use any type of letter except for S as a variable, but then you have to list down here what are the letters that are variables that are going to be solved for. So that's what this is for the symbolic params. Next, you'll enter your start frequency in radians per second and your end frequency. Again, like I said, you probably would want to use the start and end frequencies of your system ID mode run, which is the SID F start hertz and SID F stop hertz. But remember, you'll want to convert those to radians per second to put them into these fields. And lastly, you then enter your frequency cutoff for the low pass filter to condition the data. So here's some results that were shown for this particular run. So again, recommended performing the analysis on the frequency limits used in the system ID mode. You can then look at the coherence, and that's what was done here. You can then look at the coherence, and you can see the coherence is best from, so above 0.6 is what they consider good coherence. And again, coherence describes how well the output is represented by the input or output corresponds to the input. And so above 0.6 is generally good coherence. So you kind of choose about the first time you see it go above 0.6 and relatively remains above 0.6. And then you can go to where it stops and goes below 0.6. So it's for this data, it's from like 1.5 radians per second to about 60 radians per second. So almost up to 10 hertz. And so you can then change your data, and we kind of modified it a little bit more and tightened up the frequency range. We still left it at like 1 for the low, 1 radian per second, but then I cut it off at maybe, looks like I cut it off like 40 radians per second. And so you see we got a pretty decent fit. And so the other thing is remember, since this takes a little longer time, you'll see you may hit the submit button, and it's probably maybe take up to 5 minutes to run the max number of iterations if it doesn't solve it sooner. It's looking for a cost function less than 50 to consider it good. And cost functions generally less than, and so this found better solution here in the results, saying it's 24.6. That is the cost function. And again, it's looking for that to be less than 60. Here for this output or for this solution, it took 4 iterations. This is basically giving the results here is a one vector, tells you what the cost function is, and then gives you the numerator values for the s squared, uh, the s, and then the constant. And then here's the denominator for the s to the fourth, the the s to the third squared, the s, and then constant. And lastly, it also actually gives you a the the time delay as tau that it computes. And here's fairly low time delay, 2 milliseconds. So very small time delay. You almost probably could get rid of that. But in any case, here's the final transfer function. I took and made this term as the fourth one, so I multiplied everything else through to make to give you nice whole numbers there. Or in any case, and then here's your time delay here as an e to the 0.0021s. That's how it's represented. And you can see you have fairly good fit over the full range, both for amplitude and phase. All right, so what's this gravity compensation term that you're seeing feature? So basically, when you're trying to estimate the lateral acceleration or longitudinal acceleration, you have to remember for those two axes that the roll and pitch of the aircraft will affect the body acceleration and affects those um, body acceleration uh, equations of motion. And so for if you wanted to use this transfer function term to kind of estimate what the transfer function would be for the, let's say in this case it's the lateral acceleration to the roll input. You'll want to use this gravity compensation to then add that term that says, hey, it's g times phi in here that because ay itself does not include the acceleration due to gravity for that equation of motion, and so you're going to use that to calculate that what we call v dot in this case. And so in this case there, I add the gravity compensation. I have my numerator as just being a constant. The denominators going to have the highest order of two. And then I can go ahead and set up the rest of it. Note that my frequency start and stop is much lower. Generally, you'll see a much lower range of frequency when we're talking about um, the lateral and longitudinal equations of motion. And so here's the data again. You could perform it on a full range initially, and then you can kind of see where you can see the coherence is much lower, or the range that it's got good coherence is a much smaller frequency range. And then, perform it just on that frequency range and hopefully get a better result. All right, so system identification features. This supports only single input, single output, or single input, multiple output. We don't yet support multiple input, multiple output identification. So there's a manual setup or a selectable setup that has kind of a predefined setup, I'll call it, for common vehicle model structures. And so what's shown here is kind of a typical, what was considered a typical model structure for the lateral axis of a multi-rotor. So here's your first derivative of your states times your A matrix times the states plus your B matrix times your input. So for multi-rotors, we generally are using this lag term in here to represent what's typical for multi-rotors is this lag from the input to the response. And also what we notice for multi-rotors very commonly is that the YP and LP derivatives are generally very close to zero. So to improve the fit and improve how quickly it arrives at the models at the result, you basically just set these to zero as a first cut, and then solve for this model structure with those set to zero. So to do this, you'll go and start off by choosing the file that has the time history data that you want to use, and then look to set the time, start time and end time. Again, in this case, it's for the roll. We're going to start at 300, and we'll actually include up to almost 400. The system ID went longer than what than the 370. It's actually almost out to 400, or a little over 400 here seconds. Uh, After you do that, you go down below that this plot, and you'll see the choice between transfer function and state space. You'll select state space, and now you'll see that some fields appear. So here we can choose either a manual entry or push this and be able to select uh, an entry, pre-populated entry of either mainly here is just multi-rotor um, selections that are basically pre-populated fields. So, okay, so let's see here. If not using pre-saved setups, if you don't use the pre-saved setups, then you're going to have to enter the number of outputs. You'll have to enter the order of your matrix. So basically the number of states that you're going to use for your setup. You have to enter all the parameters that you wanted to determine results for, and if you have any constraints. And then you click the generate fields. But if you click the pre-populated value, let's say multi-rotor roll, you'll just hit generate fields, and then it'll come up and basically pre-populate everything that you'll need to do the analysis. So here we're going to be for this. Remember, this is the state space model. I've just inserted in here. You're not going to see this in the actual on the actual form, but this is kind of just showing kind of what we're doing here. So outputs, we have two outputs. This is really the observed variables. One is going to be the lateral acceleration and v dot. So this accounts for the roll attitude, and it's the acceleration imposed due to the gravity vector. And then we have roll rate here. So those are the two observed variables. And so basically we'll say those are our outputs. Matrix A order is essentially the number of states that we have. So it's going to be 4. We have the variables that we're trying to solve for. What are the parameters we're trying to solve for? And those are shown here in red. And you'll note that the W lag and the WLG are essentially the same value, except they're opposite in sign. And lastly, what are the constraints? And again, that's the constraint here, omega lag and omega LG. These are essentially going to be the same, except they're opposite sign. So you can specify that. So we say we have one constraint that we want to make here. And we only really have the ability to do simple constraints at this point, which is set two variables equal to each other. Next, we can put our input variable. So we're going to identify the bare airframe model, and we'll use the input to the motors class. So it'll be rate R out. We'll then set up the outputs, which are going to be the roll rate, gyro roll rate. So SID GX, and we're going to do it in radians per second. So we're going to use the multiplier times times the conversion from degrees per second to radians per second. That's shown there. The second one is the V dot, and so to get again this lateral acceleration, which includes the roll and the effect of gravity on the body axis acceleration. So we basically choose the AX, which is the accelerometers lateral acceleration, and then add that gravity compensation. So that's going to add that in there for you. Next, we specify the variable names for our parameters that we want it to solve for. And so all those are put inside there, 1 through 6. We then can specify the bounds for these variables, and this is very useful to help kind of help it get to a better solution, is knowing kind of what these variables values, what the values of these variables and what the sign of these variables should be is very helpful. And that will allows you to better, I mean, I've basically thrown in there, we've thrown in there kind of basic bounds, but you then could further like uh, and LV is typically negative. So you might want to put that you have a negative value in there. You know, what's else? L delta lat, or so L lat, which is your lateral sensitivity derivative. That's positive, and we know it could be somewhere between 50 and 200. So these are the basically want to enter your bounds in there to help the solver kind of converge on a solution much quicker. And lastly, you'll set up your matrix for your A matrix using your variables that you've specified above to put them inside your A matrix. So basically, here's my A matrix that we for the setup, and so that's what it did. It threw the values of the variables in the A matrix here. Um, And again, the input for the B matrix, and I guess I should mention that I'm just going through this to show you how it set it up for the pre-populated. If you were doing this manually, then you'd have to enter this stuff in. But pre-populated, these values are already in there, and all you're really gonna have to do is come down to the bottom here and do your start frequency, end frequency, and cutoff, and then hit submit. It's really all you should have to do for this particular if you're using the pre-populated fields. But I'm just kind of going through it to show you kind of how it, where it's pulling the information from if you had a strict model structure that you're working from. So here, the input, the B matrix variable, since already done it, right? But it's just going to be this omega LG that goes in there. And then kind of the things is a little bit more, are not as self-explanatory as this constraint. Here it's showing that that the omega lag is equal to minus omega LG. And so it actually is specifying kind of the matrix location in this format as A underscore 3 underscore 3. And then it's equivalent to the B matrix uh, and variable, which has the format of B underscore 3 underscore 0. So it's just how this is set up. You're basically, if you do your own model structure, you'll have to basically determine what position your variable is in the A and B matrices that you're trying to set equal to each other. Have to work on making that a little bit more user-friendly in the future. So now we have to tell it, remember this equation here that relates y to your states, or basically your output, observed output variables to the states in your matrices. And so H0 is the first one, and you can see across the top here, it has your states V, P, Phi, and delta lat prime. And then the outputs that you're observing are, we specified that it was roll rate and lateral acceleration. Well, remember, H0 is to relate the observed variables to the states that are not time derivatives of the states. It's just the states. So here you're going to put a 1 in this position to say that the first output is equal to just roll rate, right? And then for the second output, it's V dot. So you're going to use H1 matrix to then say that V dot here, you put a 1 there to say the V dot is equal to the output 2. Hopefully that makes sense. Next, again, you'll enter your start frequency. Typically, you want to use the frequency range you want to fit for. And so you have your lower end frequency and your upper end frequency. Again, good first cut is the start and stop frequency used in the system identification. And then you have your cutoff frequency for the conditioning of the data. Then lastly, you'd hit submit. And again, if you were just using the pre-populated, um, one of the pre-populated structures, uh, literally all you'd have to do is select that pre-populated structure, come down, and then put in your start frequency, end frequency, and cutoff frequency, and then hit submit. And it's pretty much that easy. So again, the results may take 5 to 10 minutes to come up. Be patient. It's going to do a max of 50 iterations. If it comes up with a cost uh, less than 50 quicker than the max 50 iterations, so it might take less time, but just be prepared that it might take longer. So here's the cost value here for this solution is 41. And here's our eigenvalues for this solution. As you'd expect, this is not a stable system. Typically, we have unstable systems for our multi-rotors, and so then it gives you what each of the variables are, and then puts those variables inside the A and B matrix to show you where they're located. As you can see over here to the right, I actually separated, they're all kind of put on top of each other. I actually was able to pre-select some of them to get rid of some of them and basically just show the ones for each of the axes. So this is um, the transfer function or the relationship of roll rate to R out. And then this is a relationship of V dot to R out. Right? It's both amplitude and phase. And then there's your coherence. And you can see it's only from 1 to maybe 10 radians per second that this is really valid for. All right, lastly, I think that's it. Okay, that's all. So hopefully you found that useful and helps you work through setting up your own um, solutions for transfer functions and using the web tool to find solutions for transfer functions um, and estimating a state space uh, solution. So thank you. Have a good evening.